Hello, and welcome to a lecture on geometrical optics. I'm Steve Ellingson. Here's an overview of this lecture. First, I'll introduce you to the geometrical optics concept, which I'll frequently abbreviate GO. I'll talk about the GO spread factor, GO reflection. Then I'll compare GO to the stationary phase evaluation of the physical optics integral. And this is something we covered in a previous lecture, so it's worth exploring it now in the context of this new technique, GO. Then we'll talk about GO reflection of incident spherical waves from 3D surfaces of arbitrary curvature. And this is just what we need to do large reflector antenna problems, as well as other problems that involve electrically large surfaces. Okay, the GO concept. GO is a ray optical theory of electromagnetic propagation. Essentially, it is physical optics for cases in which Ka, that is 2 pi a over lambda, is large. Now, when we say A, we're referring to the relevant dimensions of the problem. So we're saying the problem is electrically large. So we mean surfaces have large radii of curvature, at least compared to the wavelength. And we're talking about high frequencies at which that can occur. So geometrical optics is physical optics in cases where we can apply stationary phase to obtain closed form expressions. And we do that one contribution at a time, and we interpret those as the ray contributions. In GO, there's only two things that can happen. You can have line of sight propagation, that is propagation from point to point directly, or you can have reflection. So if you have 2 points, a transmitter and a receiver, and some surfaces out here, the things that can happen are that you can go line of sight, you can have reflection, and you can also have reflection over here. It is not precluded to have multiple reflections, so you can have a reflection that does something like this, multiple reflections. But you're limited to simply line of sight and some number of reflections. Because GO doesn't know anything about edges, and this is because it's related to physical optics and the stationary phase interpretation, there is no diffraction. To do diffraction, or to include diffraction, you have to acknowledge the edges or the finiteness of objects. The reflection depends only on the properties of the surface, namely curvature and materials, at the point of reflection. So 3 important ideas here. Reflection depends only on the nature of the surface at the point of reflection, or you could reinterpret that as at the stationary phase point. And the relevant properties of the surface are, of course, the materials involved and the curvature. And remember, when I say curvature, this is really 1 over radius of curvature. GO finds numerous applications in the design of large reflector antennas, especially large dishes. So, for example, simple dishes like this where we have a feed. Every time a ray reflects off the main reflector, that's geometrical optics reflection. GO also lets us do problems like this, where perhaps we have a Cassegrain type reflector. A Cassegrain type reflector is a reflector where the feed is at the vertex of a large reflector. There's a subreflector up here, so what happens is rays come in this way, bounce off the main reflector, bounce off the subreflector, and then arrive at the feed at the vertex of the large dish. The reason I mention it is because geometrical optics is just what you need to conveniently analyze these ray paths and then to determine the associated fields. Okay, a geometrical optics field is completely defined by just three basic properties. The first one is the direction of propagation. We'll often refer to this as little s hat. In some cases, I might refer to it as k hat. I may have done that in a previous lecture. Then the polarization. What direction does the E vector point? What direction does the H vector point in? In geometrical optics, everything is very simple because polarization and direction of propagation are related by the plane wave relationships. Remember what those relationships are all about the fact that direction of propagation, E, and H are related as shown in this diagram, right? E cross H gives you the pointing vector, which is the direction of propagation. And then given E, you can get H from a simple relationship and vice versa. The third property, just to be clear, 3 properties, 1, 2, and 3, is wavefront curvature. Now, the curvature of a geometrical optics wavefront requires 2 parameters to completely describe. Now, this requires a little bit of explanation for most people because most people have not been exposed previously to differential geometry. But let me explain what I mean. If I have a spherical wave that's emanating out from some point, and I look at a surface of constant phase, then I consider the radius of curvature in every plane that's perpendicular to the normal. I measure the same radius of curvature, namely the distance from the source. However, if this is not a spherical wave, if it is instead a cylindrical wave, what happens instead is I measure this as the radius of curvature in the plane that I'm showing here, but I measure 0 curvature, that is infinite radius of curvature in the other dimension. Let me kind of draw this. So here is a picture of the constant phase front of a cylindrical wave. So if I measure the curvature of the phase front, in this dimension, I measure the radius of that cylinder. But if I measure the curvature in this direction, I measure infinite radius of curvature. That is 0 curvature. So I get 2 very different numbers. Now, these 2 dimensions correspond to what's known in differential geometry as the principal planes. The principal planes are the planes which are perpendicular to the surface normal and which yield minimum curvature and the maximum curvature. So here we have the minimum curvature, that's 0. Here we have the maximum curvature, that is 1 over the radius of this cylinder. So that's what I mean by principal planes. The principal planes of a spherical wave are any 2 planes perpendicular to the normal, so the curvature in the 2 principal planes of a spherical wave are equal. Now, of course, the reason for bringing this up is because it commonly occurs in more advanced antenna problems with large reflector antennas that we do not have simple spherical waves or simple cylindrical waves. What we have instead is phase fronts which are curved in both dimensions. So I can think of some propagating tube of energy, and it's got curvature in one direction and a different curvature in a different direction. I can still define a normal to that surface, the surface being the surface of constant phase, and that's of course equal to the direction of propagation. And then the principal planes will be the planes in which this curvature are maximum and minimum. In the 2D case, there is only one parameter describing wavefront curvature. That is because all waves in 2 dimensions are in some sense cylindrical. That is, one of the 2 principal planes exhibits 0 curvature. Okay, propagation of the geo field. Here it is in 2 dimensions. Now in this picture, what I'm showing is some geo field radiating out this way. It's a 2-dimensional problem, so you can either think of this as being flatland or you can think of this as being a cylindrical scenario. They're the same result in this case. At some distance rho from wherever it is that this seems to be emanating from, we can measure a power density, and we'll call that power density S0 in watts per meter squared. And that power density is realized over a cross-sectional area, and we'll call that cross-sectional area d sigma naught, where the d is alluding to the fact that this is a differential surface area, because we're really talking about what's happening along a ray. And then we have the electric field at that point, E, and this 0 here is referring to the variable S. S equals 0 is at this reference point. It's not the origin of any particular coordinate system, it's just a starting point. And then we measure increasing S as distance traveled along this ray. So that at some later point, we can measure an electric field, which is E at S. And at that point, the power density is given by S, not S naught. And the differential area over which we're measuring this power density is d sigma. So here I've written the expressions for the power density at both the reference plane, or the reference point, and the actual point. So at the reference point where we start, we have S naught equals the magnitude of the electric field at the reference position, magnitude squared, divided by 2 times the wave impedance, eta. And then at distance S, after traveling a distance S, we have the new power density, S, big S, which is equal to the magnitude of the electric field measured at that point, magnitude squared, divided by 2 eta. Okay, so now we can invoke conservation of power. The idea is this: as we consider this expanding ray tube, whatever power we see crossing this area must be equal to the power we see crossing this area. So conservation of power requires that the power density at the reference position times d sigma naught equals the power density at the later position times d sigma, right? Because of units of watts on both sides. So those quantities have to be equal. That's conservation of power. So we can write that the magnitude of the electric field at distance S is equal to the magnitude of the electric field at the starting point times this ratio, or the square root of this ratio, and it's the square root of the ratio of the areas. And this comes directly from looking at these relationships. So what we see is that as we get further and further along this ray, this distance, this area here is getting bigger. This area here is staying the same. So the electric field magnitude is decreasing with increasing distance, as you'd expect, and it's decreasing the right way, that is, to satisfy these relationships. From geometry, we also see that d sigma naught over rho, that's the distance to the starting position, equals d sigma divided by rho plus s. Rho plus s is this whole distance here from the apparent source of this ray tube to the point that we're interested in. In other words, the area here divided by this distance is equal to the area here divided by this distance. That ratio must be equal. So if we put this all together, we can write an expression for two-dimensional geometrical optics propagation that looks like this. The electric field at some distance along this ray tube is equal to the electric field at the starting point times a phase factor. This is easy to understand. This is just the expected phase factor associated with a plane wave propagating distance s. And then this thing, which is simply this expression. Rho from this part, and then rho plus s from this part. We call this whole thing the square root of rho divided by rho plus s the spread factor. The spread factor quantifies the reduction in power density with increasing distance. So now we can do this in 3 dimensions, and it's really not that much more difficult. Here's the new picture. In 3 dimensions, we have 2 curvatures to consider. The picture that normally comes up is this picture, which is referred to as an astigmatic ray tube. So you may know from optics, astigmatism is a deviation from an ideal spherical surface. Here we have an astigmatism in the sense that the curvature in 1 dimension, and here it's called rho 1, is different from the curvature in another dimension. We'll call that rho 2. So if you go to the reference position where s equals 0, you have one apparent distance from the source, which is called rho 1, which we were just calling rho before, and then a second distance, rho 2, which also seems to come from a source, but now it's describing the curvature in another plane. So rho 2 is describing this curvature, and rho 1 is describing this curvature. Curvature in 2 different planes. However, the basic relationship does not change. The magnitude of the electric field at some point S, further on, should equal to the magnitude of the electric field at the starting point times the square root of the ratio of the areas involved. What is different in this case is those ratios. So at the reference point, at the starting point, d sigma naught, instead of dividing by just one curvature, we'll divide by both curvatures. And that has to be equal to d sigma, this area out here, divided by both new distances. Not just rho plus s, but rho 1 plus s and rho 2 plus s. And if you consider this diagram for a moment, hopefully you can see that. There's another thing that pops up here, and I should mention it, this idea of a caustic. A caustic is any point in a field in which an infinite number of rays is expected to traverse. For example, here we have a point where we see that an infinite number of rays must go through that point. So that's referred to as a caustic. And in fact, here we see a caustic in this direction, and we see a caustic along here. So they're called line caustics. And I should point out that geometrical optics is wrong at caustics. So at the caustics, geometrical optics always gives the wrong answer because it predicts an infinite number of rays propagate through those points, which gives you an infinite field, which is clearly wrong. Okay, so putting this all together, here's the 3-dimensional geometrical optics propagation equation. What we find is the electric field at some distance s is equal to the electric field at the starting position, that's where s equals 0, times e to the minus jks, the usual phase factor. And then here is the entire new spread factor. So this is what is commonly referred to as the spread factor. And all the spread factor is doing is describing the reduction in power density with increasing distance as power is being diluted through increasing amounts of area. 2 important special cases to note here. You can go from this general expression for 3 dimensions back to 2 dimensions simply by letting one of the radii of curvature go to infinity. Now here I've said rho 1, could also be rho 2, but you choose one of these 2 radii of curvature, rho 1 or rho 2, let them go to infinity, and you will see that you get the 2-dimensional expression back. If you let rho 1 go to infinity, you'll find that this part disappears in the limit, and then you're back to the 2-dimensional expression. Another important special case to know about is when those 2 radii of curvature, rho 1 and rho 2, are equal, then you have spherical waves, right? In the spherical wave case, you can see very quickly that the new spread factor is simply rho over rho plus s, no square root.